So we just saw where we measure the daughter products in the uranium, thorium, helium system on the helium analysis machine. And that's the first thing that we measure. But of course, to calculate a date, we also need to know the parent isotope concentrations. In this case, we need to measure the uranium, thorium, and samarium content of our crystals. The technique requires us to understand the total amount of uranium, thorium, and samarium in our crystal. So to do that, we actually dissolve the entire crystal. We do that process up in a clean lab, which is an environmentally controlled laboratory up on the 4th floor. We're probably not going to go up there and view that today because you have to get a lot of safety training and you have to get all gussied up in a bunch of clean workwear to go in there. Mm-hmm. But after we do the dissolutions, what we're left with is something like this. So this is it's a clear solution, and what this is one zircon crystal, one of those little metal packets we saw in there, with one zircon crystal in it, that's been dissolved using an acid vapor dissolution technique, where it takes about a week and a half under pressurized boiling hydrofluoric and hydrochloric acid. We then dissolve it, that dissolves the crystal, we then dilute it up, and we get this solution. It's about 2 milliliters of sample with one zircon dissolved inside of it. The zircon has been spiked so that we, just like with the helium system, we can measure the total amount. And then what we're going to do is we're going to measure this using this machine over here, which is called an inductively coupled plasma mass spectrometer, or an ICPMS is probably the term that maybe you've heard before. These are incredibly common machines in earth sciences. They're used for a variety of different measurements. You can put a laser on in front of them and blast samples and measure in situ uranium lead dates. But what we do is we load these samples into this sample chamber over here. And if you can see in the back middle, there's a little Teflon straw. What that does is it goes and it sucks up about 500 microliters of this sample and puts it into the machine for analysis. So what an ICPMS does is it actually has a very similar mass spectrometer to what we saw in the helium machine, which is a quadruple mass spectrometer. That is in this chamber over here. But instead of measuring a gas, what it does is it sucks up the liquid in this tube. It enters this chamber where it's mixed with a stream of argon gas. So it forms a mist. Mm-hmm. That mist is shot through this tube into this box where it goes through an RF generator, which turns it into a plasma. Mm-hmm. Of course, what that means is that it ionizes all of the atoms. And once atoms are ionized, we can manipulate them using either a magnet or an electrical field into a mass spectrometer. So that's why they call it an inductively coupled plasma. It's an induction coil that creates the plasma. Mm-hmm. The plasma contains argon gas and then whatever is in your sample, and it's shot into this mass spectrometer. These machines are incredibly quick. We can measure this sample thousands of times, which is how we do it for counting statistics, in about 2 minutes.
Wow.
It will measure the entire periodic table for us for the most part. It won't do gases, but do most everything else. But it's also incredibly precise. The concentration of these solutions are down in the part per trillion or part per quadrillion range for uranium and thorium. Remember, a zircon crystal itself may have 1,000 parts per million. That's a tiny crystal. By the time I dilute it up into this, we're down into the part per trillion or part per quadrillion level. And we can measure that easily with very good precision on these machines.
Cool.